Hey everyone! So in this video I like to talk about inverse trig functions and right triangles together. So we've defined inverse trig functions already. We said that if sine, for example, is a function that takes in input values that are representing angles and it gives back values that are the y-coordinate on the unit circle, well, inverse sine does the reverse of this. And so here it takes in y-coordinates on the unit circle, and it gives back their corresponding angle on the unit circle. And similarly, cosine takes in x values from the unit circle, and again gives back angles on the unit circle. And then lastly, tangent, we saw that we could interpret the output of tangent as a slope, and so the input of tangent inverse we can interpret as some sort of slope, and the corresponding output is the angle with that slope. But we want to be careful here. So the inverse, these inverse functions, they don't apply to all of these trigonometric, to all of sine, cosine, and tangent. They only apply to a specific region of the sine, cosine, tangent graph. So these are inverses to the original trigonometric functions, sine, cosine, and tangent, only on a defined interval. So here, this inverse sine function, we said it was only the inverse of the sine function on the interval negative pi over 2 to pi over 2. This inverse cosine function is only the inverse of the cosine function on the interval 0 to pi. And then lastly, this inverse tangent function is really only the inverse to the tangent function on the interval from negative pi over 2 to pi over 2, not including these boundary values. And so let's go over a few examples just to really remind ourselves how this works. So if I take sine inverse of, and here I'm not plugging in an angle, I'm plugging in a y-coordinate from the unit circle, plugging in negative 1/2. Well, what this really is asking us to do is to look at the y value of 1/2. Look at where on the unit circle do we have a y value of 1/2. But we're only looking at this point that corresponds to an angle between negative pi over 2 and pi over 2, because that's where the inverse cosine function is defined on. And so here, the angle between negative pi over 2 and pi over 2 that results in a y value of 1/2 is this angle here of negative pi over 6. Okay, so what if we wanted to evaluate something a little bit different, like tangent of cosine inverse of negative 1? Well, first we go ahead and try and compute this cosine inverse of negative 1. This is asking us, okay, so here's the x-coordinate on the unit circle. So here, well, this point has an x-coordinate on the unit circle of negative 1. Right, because this is the point negative 1 comma 0. And so cosine inverse is going to give us back the angle that corresponds to this x value of negative 1 on the unit circle. And this angle here is pi. Right, cosine inverse returns an angle between 0 and 1. And so what we're really doing here is we're evaluating tangent of pi. And so what is tangent of pi? Well, I mean, maybe let's remind ourselves what tangent even is. So tangent of pi, well, that's sine of pi divided by cosine of pi, which is, what is that? Sine of pi is 0, cosine of pi is 1, this is 0. And also you can think of tangent of pi as, well, if we look at this angle of pi, what's the slope of that angle, right? Tangent tells us the slope of the angle we're inputting, and that slope corresponds to, that's a slope of 0. So we've also viewed trigonometric functions in terms of right triangles. For example, our tangent function, if I took tangent of some angle, let's say here theta is this angle in this right triangle here, well, it's the opposite side to that angle divided by the adjacent side to that angle. Right, so here if this triangle was a 3, 4, 5 triangle, 3, 4, 5 right triangle, then tangent of theta in this case is, well, the opposite side length is 3, divided by the adjacent side length, that's 4. This is 3 over 4. And so the inverse tangent function, well, it sort of goes backwards from the tangent function. And so, knowing that tangent of theta is equal to 3 over 4, this also goes with this idea that inverse tangent of, well, right, tangent takes an angle and gives us a ratio, or gives us a slope. And inverse tangent is going to go backwards. It's going to take in a ratio of side lengths of a right triangle or a slope. And so in this case, maybe 3 over 4, and it's going to give us back an angle. And so here, tangent inverse of 3 over 4 is like asking, what's this angle in this triangle, which has an opposite side of 3 and an adjacent side of 4. And so in this case, inverse tangent of 3 over 4 is going to give us back whatever the value of this angle is. And this isn't something we know from our special right triangles. If we wanted to really compute this, we could use a calculator. But inverse tangent of 3 over 4 is that angle. That's what that number would be. And I keep writing equals, but here if we run this into a calculator, we actually are getting an approximation of 0.6435. So if we take a look back at all of our inverse trig functions, we could sort of interpret their inputs a little bit differently if we wanted to, right? So we said sine, takes in an angle, and if we're thinking about right triangles, it can also output that ratio, the opposite over hypotenuse. And so inverse sine, we can also not only think of it, the input as a y-coordinate on the unit circle, but we could also think of it as the ratio, the opposite side divided by the hypotenuse in a triangle. And similarly, if cosine is going to take in an angle and output the ratio adjacent over hypotenuse, we can imagine inverse cosine reversing that and taking in the ratio adjacent over hypotenuse. We can interpret the input of our inverse cosine function as that ratio for imagining right triangles here. And similarly for our inverse tangent function, like we saw a moment ago, we could think of its inputs as opposite over adjacent sides of a triangle. And so we can use this idea to evaluate compositions of trig functions and inverse trig functions. So let's say I wanted to evaluate secant of inverse sine of 12 over 13. Right, so our sine function, it takes in angles and it gives back y-coordinates on the unit circle, or opposite over hypotenuse if we're thinking about triangles. And so what we can do is we can think of inverse sine, right? It's reversing that. It's going to take in opposite over adjacent, or opposite over hypotenuse sides of a right triangle, and it's going to give back an angle. Right, so I can visualize this 12 over 13 as the opposite side length of some triangle, and the hypotenuse side length of some triangle if I've got some angle. Here is theta. Right, sine of theta would give me 12 over 13, and sine inverse of 12 over 13 would give me back that angle theta. Right, it would reverse the sine function. And then here, we can plug into a calculator 12 over 13 into an inverse sine function in a calculator, and we get some approximation for this value, and then we can run that through the secant function, and we get a new approximation. But we can actually find the exact value of this expression here, right? So here, right, this sine inverse of 12 over 13, that's that angle theta, and I can compute secant of theta by figuring out well, secant is the reciprocal of cosine, so I would need to figure out the adjacent side length, and then I would take my hypotenuse and divide it by that adjacent side length to determine secant. Right, so what is a side length? Let me give it a name. Let me say it's a. Right, so here we know the Pythagorean theorem says a squared plus 12 squared is equal to 13 squared. So we have a squared plus 144 is equal to 169. If I subtract 144 from both sides, we get a squared is equal to 25, making a, well, we would take plus or minus square root of 25 to get plus or minus 5, but here we're just talking about some triangle. So here this is a is equal to 5. So here if we compute secant of theta, without even knowing what theta is, we don't really need to know what theta is, we just know that theta is referring to this angle here of this triangle. Well, secant of theta is hypotenuse over adjacent, right? It's the reciprocal of our cosine function. What we get out here is, well, the hypotenuse is 13, and the adjacent side is 5. So what this is saying, maybe I'll just kind of put it all in one big line. So secant of sine inverse of 12 over 13, this is equal to 13 over 5. This big messy statement, we're able to figure out exactly what the value is. No approximation, no calculator necessary, just by interpreting this input as the sides of a right triangle. Okay, so let's take a look at one more example here. We want to find the exact value of cotangent of inverse cosine of 2/3. So let me encourage you to pause the video and try this example out yourself first before we do it together. So here we're saying that this inner function, this inverse cosine of 2/3, we can sort of view that in terms of this right triangle. Right, cosine takes in an angle and gives back out the ratio adjacent over hypotenuse. And so inverse cosine is going to do the reverse of that. It's going to take in a ratio of side lengths over right triangle, the adjacent over hypotenuse, and it's going to give us back some angle. And so if we want to find cotangent of that, we just need to figure out what cotangent of that angle would be, without actually having to evaluate that angle, right? So cotangent would correspond to, well, tangent is the opposite over adjacent sides of a right triangle. Cotangent would correspond to the adjacent over the opposite side of a right triangle. And so in this picture here, if I imagine this is a right triangle with a side length of 2 and a side length of 3 here, and this is my angle theta, right? Cosine of this angle would be 2 over 3. And so cosine inverse of 2 over 3 would give me back this angle here. And so really to evaluate our expression, we just need to figure out what cotangent of this angle is. And so we need to figure out, well, we have the adjacent side, that's great, but we need the opposite side now. If we can find the opposite side, we can find this ratio, and we would compute, we would have exactly the value of this expression here. And so what's this missing side length? If I label it b, well then I know that 2 squared plus b squared is equal to 3 squared, right? Just the Pythagorean theorem here, and we have 4 plus b squared is equal to 9. So that makes b squared 5, and b would be plus or minus the square root of 5, but we're just talking about some side length of a right triangle here, so here we can go ahead and label that square root of 5. And so cotangent of theta, right, theta being cosine inverse of 2/3, well, it would be the adjacent side over the hypotenuse, not the hypotenuse, the opposite side, so that would be 2 over the square root of 5. And so something else that comes up with compositions of trigonometric functions and inverse trigonometric functions is sometimes you'll deal with an expression. You might not be asked to actually evaluate, but you'll just be dealing with this composition expression. And we can actually convert this into an algebraic expression without any trigonometric functions here, by sort of doing exactly what we did earlier. And so here, if we take a look at the same, this trigonometric expression, and we use our same idea here that inverse cosine, it takes in inputs that are ratios of right triangles, the ratio adjacent over hypotenuse, and it's going to give us back some angle theta. Well, here let's look at x as this ratio adjacent over hypotenuse, and it might be easier if we look at x as x over 1, right? Any number is the same as itself divided by 1, and so I can think of this as this numerator here as being the adjacent side to an angle in a right triangle, and this denominator here as being the hypotenuse side in this right triangle. So here, if we got an angle theta here, and I have a side length adjacent to my angle theta is x, and my side length of my hypotenuse is 1, then cosine inverse of x is going to be exactly this angle here, this angle theta. And so if I want to evaluate tangent of inverse cosine of x, really I'm evaluating tangent of theta here. I need to figure out what the opposite side length is, at least an expression for it, and then divided by my adjacent side, and that would be an expression for tangent of inverse cosine of x. Right, so here, let's go ahead and figure out that opposite side length. So here, let me call it b for a moment. We know that x squared plus b squared is equal to 1. And so here, we're looking for this missing side length b, so we want to figure out, we want to solve or isolate this b. So let's subtract x squared from both sides, giving us b squared is equal to 1 minus x squared. And that would make b equal to plus or minus the square root of 1 minus x squared. And so here, again, we're looking at the side length of some right triangle here. I'm just going to leave it as 1 minus the square root of 1 minus x squared. And so if cosine inverse of x is going to give me this angle theta, then tangent of that result, tangent of theta, would be, well, the opposite side divided by the adjacent side. So here, really at the end of the day, tangent of cosine inverse of x, well, that's equal to the square root of 1 minus x squared over x.